If an external force disturbs an aircraft from a steady state of flight, it is stability, built into the aircraft by the designers, that gives it the tendency to return to a steady state of flight without any help from the pilot. In this regard, all aircraft must have several qualities. Firstly, the aircraft must have enough stability to maintain a steady flight condition. In other words, the pilot can't be made to feel that the aircraft is balanced on the head of a pin, ready to head off into some strange attitude. The aircraft must also have the ability to recover from various disturbing influences by itself. An example of a disturbing influence is a gust of wind. The aircraft must also have proper response to the controls throughout the entire flight envelope. The study of stability is broken down into two categories: static stability and dynamic stability. Static stability is the initial reaction of the aircraft following removal of the disturbing force. Dynamic stability is what happens after the initial reaction. We will start with static stability and consider dynamic stability later. There are three types of stability: positive, neutral, and negative. To demonstrate positive static stability, we will consider a ball in a bowl. The ball is stationary in the bottom of the bowl. The ball is in equilibrium. As a reminder, equilibrium exists when the sum of the forces is zero and the sum of the moments is zero. The ball has been displaced from equilibrium by a disturbing force. When the disturbing force is removed, the initial reaction of the ball is to start back towards its previous state of equilibrium, a demonstration of positive static stability. You are probably thinking a ball would not just stop like that. No, it wouldn't. Although dynamic stability will be discussed later, it will help to have an insight now. As soon as the disturbing force is removed, the ball will return through its previous state of equilibrium until friction and air resistance damp out the motion. It will eventually stop moving in its previous state of equilibrium. Everything after the initial reaction is dynamic stability. Let's now consider neutral static stability. The ball is in equilibrium on a flat level plate. A disturbing force displaces the ball from a state of equilibrium, and when the disturbing force is removed, the ball remains in a new state of equilibrium, a demonstration of neutral static stability. Whenever a disturbing force moves the ball and then the disturbing force is removed, the ball remains in equilibrium. Now for a look at negative static stability. The bowl is inverted with the ball in equilibrium. The ball is displaced from equilibrium by a disturbing force. When the disturbing force is removed, the initial reaction is for the ball to displace further from equilibrium, a demonstration of negative static stability. We must now consider the aeroplane reference axes. These are used to help visualize the forces and moments on the aircraft. All axes pass through the center of gravity. Illustrated is the longitudinal axis. Here is the lateral axis. And this is the normal axis. The aircraft rolls about the longitudinal axis. In the context of stability, motion about the longitudinal axis is called lateral stability. An easy way to remember which is which is to add the axis about which the aircraft rotates. In this case, lateral stability is about the longitudinal axis. The aircraft yaws about the normal axis. Motion about the normal axis is called directional stability, the easy one to remember. The aircraft pitches about the lateral axis. Motion about the lateral axis is called longitudinal stability. Again, to fix in your mind which is which, add the axis about which the aircraft rotates. In this case, longitudinal stability is about the lateral axis. We will study longitudinal static stability first, because pitching motion does not interfere with either rolling or yawing. We know that the center of pressure moves when the angle of attack changes. During our study of stability, we will be considering changes in angle of attack, together with various center of gravity locations. To aid understanding, a location called the aerodynamic center is used. Don't think of this as a wing. This is merely a concept. To help you understand the concept, think of the aerodynamic center, the AC, as a pivot. Consider angle of attack 1. Angle of attack 1 will generate lift 1, acting through the center of pressure. Lift 1 is acting at distance 1, aft of the aerodynamic center. Lift 1 multiplied by distance 1 generates pitching moment m. Pitching moment m acts nose down, about the aerodynamic center. An increase in angle of attack moves the center of pressure forward and increases the lift. Angle of attack 2 generates lift 2, acting at distance 2. Lift 2 is bigger than lift 1, but distance 2 is shorter than distance 1, such that pitching moment m will remain the same. The Greek letter delta, in front of alpha and lift, is used to indicate change. The change in angle of attack has generated a change in lift. But because pitching moment m remains the same with a change in angle of attack, we can consider the change in lift acting at the aerodynamic center. You can see that the original lift force is greyed out. We are interested only in the change in lift. There are 4 facts about the aerodynamic center in which the examiners are interested. First, the location of the aerodynamic center is stationary at 25% aft, but only in subsonic flow. During your studies of high-speed flight, we will discuss the location of the aerodynamic center in supersonic flow. Second, the direction of pitching moment m is nose down about the aerodynamic center. Third, pitching moment m stays the same with a change in angle of attack. Fourth, we consider the change in lift from a change in angle of attack to act at the aerodynamic center. The aerodynamic center will also be used in future lessons when we discuss aircraft limitations. During our study of stability, and later in aircraft limitations, we make 2 uses of the aerodynamic center. First, it is stationary at 25% aft. Second, it is the point through which the change in lift acts. Having covered some basic facts about stability, we will now apply them to an aircraft. Illustrated is the wing of an aircraft. For the time being, we will ignore the rest of the aircraft. We are in level flight, in a state of equilibrium. The flight path is shown, as are the aircraft CG, the aerodynamic center, and the greyed out lift force. An upward vertical gust has increased the angle of attack. This generates an increase in lift acting at the aerodynamic center. The change in lift is acting through arm X, forward of the aircraft CG. This generates an aircraft nose-up pitching moment, which pitches the aircraft nose up. This will further increase the angle of attack, and the aircraft will continue to pitch nose up at an increasing rate. The wing, considered in isolation, is therefore statically unstable. This illustration shows that the change in wing lift multiplied by the wing arm can be called the wing moment. As we have seen, the wing moment is destabilizing. We will now consider how the designers provide the aircraft with static longitudinal stability. The tail plane is the aerofoil that gives the aircraft static longitudinal stability. For the moment, we will consider that the vertical gust changes the angle of attack on the tail plane by the same amount as the wing. The tail plane will generate an increased up force. I know you are thinking the tail force should be pointing down, but here we are merely considering the change in force on the tail plane. All textbooks illustrate longitudinal static stability in this way. The change in lift on the tail plane acts through an arm to the aircraft centre of gravity. The change in tail plane lift multiplied by the tail arm can be called the tail moment. The tail moment is stabilizing. If the stabilizing tail moment is bigger than the destabilizing wing moment, the aircraft will have some measure of longitudinal static stability. A vertical gust has displaced the aircraft from equilibrium. But because the tail moment is larger than the wing moment, the aircraft will immediately start to return to its previous state of equilibrium, without any input from the pilot. The fore and aft position of the centre of gravity will have a significant effect on longitudinal static stability. The illustration shows a centre of gravity position at which the stabilizing tail moment is bigger than the destabilizing wing moment. The aircraft will have some measure of longitudinal static stability. If the centre of gravity moves forward, the length of both arms change. The tail arm becomes longer, which makes the stabilizing moment bigger. And at the same time, the wing arm becomes shorter, which makes the destabilizing moment smaller. Therefore, with the centre of gravity in a more forward position, the aircraft has more longitudinal static stability. If the centre of gravity moves aft, the length of both arms will change again. The tail arm becomes shorter, which makes the stabilizing moment smaller. And at the same time, the wing arm becomes longer, which makes the destabilizing moment bigger. Therefore, with the centre of gravity in a more aft position, the aircraft has less longitudinal static stability. Now let's consider what would happen if the centre of gravity is moved further aft. A CG position would eventually be reached when both the destabilizing moment and the stabilizing moment are the same. If a gust were to change the angle of attack, the aircraft would be displaced from equilibrium, but no net pitching moment would be generated. The aircraft would not displace any further, but would not start to return towards its previous equilibrium either. It would stay displaced. What type of longitudinal static stability would this be? Neutral longitudinal static stability. The CG position that will give the aircraft neutral longitudinal static stability is called the neutral point. Operationally, you would never fly an aircraft with the CG on the neutral point. You might think that neutral longitudinal static stability is not too bad. But remember, the aircraft must always be flown with a margin of safety. If the CG were to move after the neutral point, the aircraft would have negative longitudinal static stability, and when hit by a gust, will continue to displace from equilibrium, which is obviously not acceptable. Having returned the CG to the neutral point, we will now consider the acceptable CG range. If we move the CG slightly forward of the neutral point, the aircraft would have a small amount of longitudinal static stability. but there would still be an insufficient margin of safety. Moving the CG slightly further forward will increase longitudinal static stability a little more, but will still not provide a big enough margin of safety. With further forward movement, eventually a CG position will be reached when the minimum acceptable longitudinal static stability exists. The CG position that guarantees minimum acceptable longitudinal static stability is known as the aft CG limit. Operationally, the CG must never move outside the aft CG limit at any time during the flight. Calculating the CG position during the entire flight will be fully covered in a different subject called mass and balance. If we now move the CG forwards of the aft CG limit, the longitudinal static stability will increase. But we don't want the CG too far forward, because there is such a thing as too much longitudinal static stability. You might think the more longitudinal static stability, the better. But no. In addition to our example gust, the pilot can also momentarily change the angle of attack when a pitch input is made. Longitudinal static stability will oppose the pilot's pitch input in the same way it opposes a gust. The greater the stability, the more the resistance to pitch input. So, in addition to the effect of CG position on longitudinal static stability, we must also consider the effect of CG position on the ability of the pilot to maneuver the aircraft in pitch, and the stick forces required. Consequently, to ensure minimum ability for the pilot to maneuver the aircraft in pitch, plus ensure the stick forces are not too high, a forward CG limit is required. The forward CG limit will give maximum longitudinal static stability and guarantees minimum acceptable maneuverability and maximum acceptable stick forces. The aft CG limit will give minimum acceptable longitudinal static stability and gives maximum maneuverability and minimum acceptable stick forces. We will now take what we have learned about longitudinal static stability and, using simple sketch graphs, consider some of the variables. Here are the two axes. The vertical axis represents pitching moment, with increasing nose-up pitching moment above the horizontal axis and increasing nose-down pitching moment below. The horizontal axis represents lift coefficient, increasing to the right. Your previous knowledge will tell you that the horizontal axis could instead be labelled angle of attack or decreasing indicated airspeed. As you will see, all three values need to be considered to give a full understanding of these graphs. For the time being, we will use lift coefficient for the horizontal axis, but you need to keep the two alternative values in mind. An aeroplane in equilibrium is shown on the horizontal axis. How do we know it's in equilibrium? Because it is not generating a nose-up pitching moment or a nose-down pitching moment. An upward acting gust has increased the lift coefficient. And because the aircraft has some longitudinal static stability, it will generate a nose-down pitching moment. The nose-down pitching moment will start the aircraft back towards equilibrium. Remember, longitudinal static stability is just the initial reaction to a change in angle of attack. The graph is reset with the aircraft in equilibrium. A downward acting gust now decreases the lift coefficient. Because of its longitudinal static stability, the aircraft will once again generate a pitching moment, but this time it's a nose-up pitching moment. The nose-up pitching moment will start the aircraft back towards equilibrium. The graph is again reset with the aircraft in equilibrium. If we join together the point on the graph that represents the aircraft in equilibrium the point that represents the pitching moment generated by an increase in angle of attack, and the point that represents the pitching moment generated by a decrease in angle of attack, the plot will represent a longitudinally statically stable aircraft. The curve on the right-hand end of the plot shows the aircraft nose-down pitching moment at the stall. Now let's use the graph to consider variations in longitudinal static stability. Movement of the red dot shows an increase in angle of attack, which generates a nose-down pitching moment. Reset the graph to equilibrium. A decrease in angle of attack generates a nose-up pitching moment. Now we'll look at a decreased level of longitudinal static stability. The same increase in angle of attack has generated a smaller nose-down pitching moment. Reset the graph to equilibrium. The same decrease in angle of attack has also generated a smaller pitching moment, but this time nose up. Now we'll look at an increased level of longitudinal static stability. The same increase in angle of attack has generated a much bigger nose-down pitching moment. Reset the graph to equilibrium. The same decrease in angle of attack has also generated a much bigger pitching moment, but this time nose up. The green plot shows longitudinal static stability. The blue plot shows less longitudinal static stability. The magenta plot shows more longitudinal static stability. The direction of all three plots is downward, from left to right. This indicates positive longitudinal static stability. The angles of the plots shows the amount of longitudinal static stability. The steeper the plot, the greater the stability. What does this plot represent? An increase in angle of attack generates no pitching moment, nor does a decrease in angle of attack. This plot represents neutral longitudinal static stability. What do you make of this plot? An increase in angle of attack generates a nose-up pitching moment. This is not good. Reset the graph. A decrease in angle of attack generates a nose-down pitching moment. Again, this is not good. When the slope of the plot is upwards from left to right, it represents negative longitudinal static stability. As with positive longitudinal static stability, the steeper the slope, the greater the instability. Here are the three types of plot we'll be using from now on: stable, neutral, and unstable. So what does this plot represent? Here's a big clue. The plot represents an aircraft with a swept wing. Stable at high speed because the plot slopes downward to the right. The plot continues to slope downward to the right as speed is reduced. But the slope is becoming less steep, which represents a slight decrease in longitudinal static stability. With further reduction in indicated airspeed, the stability becomes neutral. From your previous studies of swept wing stall at higher angles of attack, tip stall will begin. And like all swept wing aircraft, this will generate a nose-up pitching moment. In the next segment, we will be using graphs like these to illustrate other variables.